So here's this week. It's incomplete, I would say. I want to see how things go these first couple days. We'll see how Thursday and Friday go.
All right.
So yeah, 13-1 today. We're jumping to 13-4, then back to 13-2. These honestly don't build too much on one another. They're kind of separate ideas, so we're going to kind of go in a little different order, kind of the order that makes more sense to us. So today, sample space and probability. How much probability have you guys done before in previous math classes?
Zero.
Tiny bit, but I don't know.
No, I think we've done some last year.
All right.
Not do probability.
Just a little bit. All right, go ahead, write this down. A probability experiment is an action or trial that has varying results. The possible results of a probability experiment are called outcomes. If I roll a dice, what are the outcomes? Good. Rolling a 1, a 2, a 3, a 4, a 5, a 6 if it's a 6-sided die. That's just
Roll a d20.
we worked up to that.
Roll a d20 for initial. Yes. I played that.
The set of all possible outcomes is called a sample space. There's my die. For moments like this, there's my die. Just be careful if you offer one to someone. It's all on how you say it. All right, you don't want to say "want to die." Say "would you like to die?" Else it's kind of aggressive. Want to die? All right, quiet please. Quiet please. Hey guys, let's get going. All right, so as we work through this vocabulary, a probability experiment is rolling a 6-sided die. The sample space of that experiment would be anything that could possibly happen. All right, all of the possible outcomes. And like say one event, it's like something you'll be asked to calculate. Like what's the probability of rolling an even number? That would be an event. Okay, and the outcome could be rolling a 1, a 2, a 3, a 4, a 5, 6. All right. So, aren't the outcomes? Do we know the word subset? No. Subset, like for example, every person living in the world, okay, would be the entire sample space. Okay. Students in this classroom right now are a subset of that group. Okay, a smaller group. Yeah, a portion of it. Okay. So an outcome is always going to be a subset of your sample space. It's not possible to have an outcome that's not in your sample space. Do you agree? Okay. So let's get started. These will make more sense as we go. All right, you flip a coin and roll a 6-sided die. And this is happening at the same time. Okay, this is one event. I don't think I have a coin. Nobody has a coin, did it?
No.
I almost got it. That was pretty good. Thank you. Thank you. All right. How many possible outcomes are in the sample space? So here's what's happening. Okay, it's this. Okay, it's that at the same time. So don't go all random on me. All right, students tend to be random and unorganized as you list these. Because they're like, oh, well, there was a head and a 5. All right, I'm going to write that down. And then a tail and a 2. Go in order somehow. All right, so wouldn't it make sense to say all the combinations of flipping a head? Like flipping a head, rolling a 1. Flipping a head, rolling a 2. And just kind of go in order, making sure you get everything. All right, so head 1, head 2, head 3, head 4, head 5, head 6. And then tail 1, tail 2. Do Do you see how you can catch them all that way? Yes? All right. So, and they recommend drawing they recommend drawing a tree diagram. Do you know what a tree diagram is? Ready? For the coin flip, you can do a head or a tail. And then a die roll, 1 through 6, and tail 1 through 6. So our sample space is head 1, head 2, head 3, head 4, head 5, head 6, tail 1 through tail 6. How many outcomes are there? 12. Thank you. This was one outcome. Flipping a head, rolling a 1, bless you. Flipping a head, rolling a 2 is another outcome. There are 12 outcomes. So we're just practicing vocabulary and thinking of all the sample space that could be listed. Good so far? Good so far. So let's circle back. It said list all the possible outcomes. If you wanted to abbreviate, you could do H1, H2, H3, H4, H5, H6, and then T1 through T6. I would know what that means. All right. Flipping a coin, rolling a die are very common in probability experiments. All right. Next little thing I need to ask you. Go ahead. Yeah.
Are we supposed to draw the tree diagram and list the possible outcomes?
That's to help you list the possible outcomes.
Oh, okay.
It's not. That's how they recommend you get to it. But I bet you'll, if you just list them, I bet you guys would be like, oh yeah, I got them all. Do we know the difference between theoretical probability and experimental probability? Have we learned those before? Okay. Do you know what the word theoretical means? Like theory, like if.
Like it could.
Yeah, it's like general things that we have seen in patterns. Okay. What's the theoretical probability of flipping a head? But what's the probability? 50% or 1 out of 2, right? What's the theoretical probability of flipping a tail? 1 out of 2, 50%. Yes? Now, what if I flip it 10 times? What if I flip it 4 times? Let's do it. Ready? I'm going to flip it 4 times. What's the theoretical probability I flip a head 2 times out of 4? I mean, that should happen, right? Like, ready? Tail. That's flip 1. Tail. Flip 2. Head. Flip 3. Tail. Flip 2. So of those 4 experiments, okay, I flipped a tail 3 out of 4 times. Yes? What was the probability that my experimental probability of flipping a tail? It was 75%. Did I say experimental? Because it was an experiment. I actually did it 4 times, didn't I? And what was the experimental probability? 75%. What was the theoretical probability that it was going to happen that I would have flipped 2 heads? 50%, right? That's what it should be. And if I did it enough, listen very carefully, shouldn't the experimental probability get closer and closer and closer and closer and closer to the theoretical probability? Do you agree with that? That's the difference though between theoretical and experimental. One is an experiment, what actually happened. The other one is what's the theory behind it. Like there's a story about a person flipping a coin in a jail cell for however many thousand times. Have you ever heard of that? Okay, a person flipped a tail or wanted to find out the probability, and you've all heard the story probably of tails is more likely because there's the little ridges on the coin that are heavier. Have you ever heard that? No? Some people believe that. And actually someone in a jail cell did it like hundreds of thousands of times. And I should have looked this up because I wasn't planning on telling the story. But they actually got tails a little bit more. From what I heard, I did not look into it. I did not watch them flip the coin. Fortunately, I was not in the jail cell with them. But that's the story. All right. So what does it mean to be likely or unlikely? Well, these are theoretical probabilities. If you are, this book is saying in the 75% range to 100% range, you're likely to certain that it's going to happen. Likely to certain. Under 50%, like 25% down to 0%, unlikely to impossible. All right. The outcomes for a specified event are called favorable outcomes. When all outcomes are equally likely, head, tail, the theoretical probability of the event can be found by using the following. The number of favorable outcomes over the total number of outcomes. So in my example, in my experiment of flipping a coin 4 times, I was trying to get 2 head flips, correct? That would have been 2 out of 4. So the probability, so if A is flipping 2 heads, okay, and the event was flipping a coin 4 times, then the probability of A would be, what would be the favorable outcome if I'm trying to flip 2 heads? Well, 2, right, out of the 4, which we knew is 1/2 as a fraction, 0.5 as a decimal, 50% as a percent. All of those are different expressions for the same thing, right? So that would be our favorable outcome. Now, favorable just means that's what you're trying to test, all right? If it's what you're testing and it happens, it's a favorable outcome. So this is read as probability of A, or P of A. All right, student taking a quiz. Ooh, this is a classic problem, right? True false quiz, gonna guess, right? A student taking a quiz randomly guesses the answers to 4 true false questions. What is the probability of the student guessing exactly 2 correct answers? Take a minute, try to see if you can list the favorable outcomes, the sample space, and then find the probability of them guessing 2 correct answers. Hey guys, don't just like think in your head. Write stuff down, okay? Write down all combinations.
Wait, you want us to put the sample space?
I think it'll really help you if you do. Tally.
So the favorable outcomes aren't getting the correct answer on all of them. It's what they asked us 2 correct answers.
Yeah, because that's what we're trying to see. What's the probability of that happening? So a favorable outcome would be getting the number of ways the student could get 2 correct answers out of 4. If that makes sense.
It does. I was just wondering.
Yep. Yeah, obviously for the student, the favorable outcomes would be get to all 4 right? But it's not what we're testing in this one. All right. Now I'll take some answers. What'd you get as a fraction? What'd you guys get? Anybody? 1/2.
1/4.
1/4. 1/4. They get something different? All right. So do you agree if you listed the possible ways a student could get 0 correct out of 4? If we called like I incorrect and like the book uses C for correct, I for incorrect, C for correct. If they got 0 correct, wouldn't it go problem 1 incorrect, problem 2 incorrect, 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 I. Yes?
Mm-hmm.
How about getting 1 question correct? Couldn't they get number 1 correct and then the next 3 incorrect? Or couldn't they get the first one incorrect, the second one correct, and then incorrect, incorrect? Or incorrect, incorrect, correct, incorrect. Or incorrect, 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 correct. Isn't that every combination of getting 1 correct answer? How about 2 correct answers? Couldn't you go I, C, and then I, C, and then I? Do you see how you need to be organized with this stuff to get all the combinations? Here's what I'm saying. I'll give you the chart. It's easier to see it. All right. Number of correct. Let's say 2. Couldn't you get the first 2 incorrect and the last 2 correct? The first one correct, the first one incorrect, the second one correct, then incorrect, correct. Does that make sense to you? How to list all of those? Some people struggle with those. Do you see it or no? All right. And then how about getting 3 correct? And then obviously all 4 correct. There's only 1 example. How many outcomes are in this sample space? Well, isn't there only 1 outcome of getting 0 correct? Aren't there 1, 2, 3, 4 outcomes of getting 1 correct? 1, 2, 3, 4, 5, 6 outcomes of getting 2 correct. 1, 2, 3, 4 outcomes of getting 3 correct, and only 1 outcome of getting all 4 correct. How many outcomes are in the sample space? 16. Do you agree? 16 total outcomes. Does anybody disagree with that? 16 total outcomes. But isn't our probability of getting exactly 2 correct? Probability of 2 correct. It's the number of favorable outcomes out of 16. How many favorable outcomes are there? Well, we're testing to see that they're going to get 2 correct, right? Exactly 2 correct. How many favorable outcomes are there? 6 out of 16. Always, well, not always. We're going to reduce this. 6 out of 16 is 3/8, which is about, and I don't want the decimal here, but I think it's 0.375. So about 37.5% chance. So they're going to get exactly 3 correct. Now say you're going into a multiple choice quiz that's not multiple choice, true false quiz. It's 4 questions and you want to get all 4 right. What's the chance you're going to get all 4 right? Well, how many favorable outcomes are there to get all 4 right? 1 out of 16. Okay? There's a 1 in 16 chance that you're going to get all 4 right if you guess. Does this make sense? How to list them all? Okay? If this doesn't make sense to you, this is this is listing like for question number 1, this is for question number 2, this is question number 3, and this is question number 4, right? I get all 4 correct. This one I got number 1 correct, but then I got 2, 3, and 4 all incorrect. Okay, that's every combination of getting 0 correct, 1, 2, 3, and 4. And do you see? I bet when I gave you some time to try this on your own, it was hard to keep this one organized into a sample space, wasn't it? Okay, that's kind of what it's part of learning this is learning how to keep things organized.
So you don't use the tree thing for this one? That's what we did. I got 16, but I didn't get the 6.
So how did you do the tree on this one?
I just put 4 true, 4, and then like I put like a check mark for true, like 4 of them, and then I put 4 X's, and I did the same for false.
Okay. The reason I don't see a tree one working for this one is because it's not like a coin and a die. It's not like 2 things that are getting merged together. It's like, I guess my mind doesn't see it like a tree, but maybe it could be. I'm not saying it's not possible. All right. The sum of the probabilities of all outcomes should be 1. What does 1 mean? 100%, right? 1 is 100%. So when you know the probability of an event A, you can find the probability of the complement, not a you look nice today kind of compliment. Complement means everything else, right? Remember finding the angle in a right triangle and then finding its complement? Complementary angles, they made up 90. Complementary probabilities make up 100%. All right. The complement of event A consists of all outcomes that are not in A and denoted by A bar, which is the complement of A. So be careful. This is P of A bar or the complement of A. P of A is the probability of A happening. Okay. P of A bar is the complement of probability A happening. Here's a quick little example. Okay. When I flipped the coin 4 times, what was the probability of tails? My experimental. 3/4 or 75%, right? What was the complement of that event? 1/4. The probability of flipping heads, right? It was only 1 out of 4. Didn't 1/4 and 3/4 add up to 1? They're complementary events. Okay. So here's a formula you just kind of makes sense. If you want to find the complement of A happening, it's 1 minus the probability of A happening. So when we said 3/4 to find out what the probability of flipping a head in that experiment, 1 minus 3/4 or 1/4. Is this one of your fill-ins? All right. Gave it to you. All right. When 2 6-sided dice are rolled, there are 36 possible outcomes. Do you agree with that or not? When 2 6-sided dice are rolled, can you guys imagine all 36 possibilities? A 1 or so ready? We'll call it a red die and a white die, because that way you can keep them straight. All right. A 1 and a 1, a 1 and a 2, a 1 and a 3, a 1 and a 4, 1 and a 5, 1 and a 6 on the white die. Okay. They went vertically, I guess. And then a 2 on the white die, and then 1, 2, 3, 4, 5, 6. And then a 3 on the white die, and then a 1, 2, 3, 4, 5, 6. Do you see how you can collect all of them that way? So there's 36 total outcomes. Find the probability of each event. All right. Find the sum of so the sum is not 6. Find the probability that the sum is not 6. Isn't that 1 minus the probability of a 6? Do you agree? Are the probability of rolling a 6 and not a 6 complementary events? I said 6, rolling 6. Rolling a sum of 6 or a sum of not 6. Complementary events. Okay. Give me one example of rolling a sum of 6. The white die is a. Let's start here.
3.
The white die is a. Sure, 3. I asked, then I said no, so whatever. Sorry. White die is a 3, and the red die is a 3. That adds up to 6. Next one. White die is a 1 and a 5. And then a 2 and a. We already did the 3, and then a white die 4, and then 5 and 1. Did we get them all?
No. I need to do 4.
What are we missing?
Red 1.
Red 1, white,
5.
red 1. Or we got that one? Did we get all 5? Sorry, I gave it away. Did we get all the combinations? Yeah, do you see how they alternate? Like we got the 1 and the red 5, we got the 2 and the red 4, we got the 3 and the red 3, we got the 4 and the red 2, and then the 5 and the red 1. Yes? Okay. So what's the probability of rolling a sum of 6? Probability of a sum of 6. 5 out of 36. And I'm going to change this, what I wrote up here in red, I'm going to change one little thing, okay? I should have put not probability of a 6 because that is kind of confusing. What should we put? Sum probability of the sum of 6. Is that easier to just do 1 minus the probability of a sum of 6? Or would you rather have counted all of the ones that don't add up to 6? It's up to you. Let's do it. Ready? 1 minus, what was the probability of a sum of 6? 1 minus the probability of a sum of 6. 1 minus 5 out of 36. I'm going to give you 2 options here, guys. Okay, just be patient. How do we subtract? Well, isn't 1 36 out of 36? So isn't this 36 out of 36 minus 5 out of 36? Which is what? 31 out of 36. 31 out of 36 is the probability of rolling 2 die where the sum was not 6. If I circled 5 up here where the sum was 6, aren't there 31 up there where the sum was not 6? Yes? I'm getting some confused looks. Please ask. Jackson.
Do we have to draw a picture each time?
No, I will not make you draw a picture, but you need to understand what the sample space is. Okay? So, option 1, you count up all the ones that don't add up to 6. Oh, there's 31 out of 36. Option 2, find the complement of the event, which I did. I found the probability that they added up to 6. And I said, well, if that's 5 out of 36, everything else must be 31 out of 36. 1 minus the probability will give you the complement. Paige, question?
No, you answered it.
Awesome. All right. Why don't you guys find letter B? Find the probability. The sum is less than or equal to 9.
Ryan Anderson.
I do. He's right here.
It's the other one.
There's another Ryan Anderson.
Other one. Yes.
Pretending to be you.
Yeah.
Well, I didn't bring you lunch. Never mind. Sorry. Excuse me.
Sorry. Anybody had Mr. DeGeorge last year?
Last year.
Well, the majority of people were.
He said,
All right. How many of you are finding the just the probability of what it asked you, and then I'll ask how many people are finding the complement and doing 1 minus. So how many people are finding it as it asked you? Just all the successful outcomes. Raise mine. All right. How many of you are finding the complement and doing 1 minus? It's about half and half. All right. All right.
Everything that's less than or equal to 9.
The sum is less than or equal to 9. Ready? Is 1 and 1 a sum that's less than or equal to 9? How about 1 and 2? Right? Got 4. Got 5. You got 6. 7. Those are all a sum that's less than or equal to 9. Yes? Got 8. 7. 6. Yeah. All right, give me a rule. Where do I stop shading?
When it's above.
Yeah, when it's above 9, right? So a 5 and a 4, would I shade that one if I'm shading the successful ones? A 5 and a 4? 6 and a 4? No. 6 and a 3? All right. Yes, 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 yes. How about a 5 and a 5?
No.
How about a 5 and a 4?
Yeah.
Yeah, 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 yeah. How about a 6 and a 4? How about a 6 and a 5?
No.
6 and a 6?
No.
Did I miss any?
No.
So, how many did I shade? 30 out of 36. Option 1. Count up all the successes, all the ones that actually describe the outcomes that we listed. 30 out of 36, which reduces into... What's that? 5/6. Yep. Now, what does that mean? The probability of a sum greater than 9. 1, 2, 3, 4, 5. 6 out of 36, which is 1/6. Yes? So how many of you did the probability greater than 9?
Well, I subtracted that.
Yep, and then subtracted from 1. That's fine. So if you did it that way, you'd be like, oh, there's 1/6, because there's a lot less to count, right? If you did it the other way, you would have counted the unsuccessful outcomes and then did 1 minus that, because it's the complement of that event. Does that make sense? Because some people are like, well, that's just a lot less to count. I'd rather do it that way. Either way is fine. All right. Let's see how many more we have left. Yep. All right, let's make a plan here. And by the way, this is, again, there's another one of this book where they have a little bit confusing picture. This is 3. This is 3. This is 3. As inches for the radii there. All right. Now this is a dartboard, so you got 10 points, 5 points, 2 points, or 0 points. And they say you throw a dart at the dartboard. Your dart is equally likely to hit any point inside the square board, meaning you have no skill. Okay. You throw a dart and it just goes equally likely to go anywhere. Are you more likely to get 10 points or 0 points? Well, how should we approach the problem? Area of the whole square, yeah, that everything. Area of the 10-point region. Now, watch up here. If we found the area of the whole square, what are the dimensions of that square? 18 by 18, correct? 3, 6, 9, that's the radius. 9 over there. 18. If we find the area of the whole square, how do we find the area of the 0-point region?
Then you subtract the big circle.
Yeah, subtract the circle with a radius of. Careful. 9 page.
Oh.
Is that what you're gonna say?
I was gonna give it. Find it.
Gotcha. What's your idea?
My idea was to find the area of the square, and then find the area of one of the circles, multiply it by 3, and then subtract that from the square.
We have to be careful here because if we find one of the circles and multiply by 3, remember, as a circle's radius increases, it doesn't increase by the same amount. Remember the pizza example? You order a pizza with a 4-inch radius and an 8-inch radius. You actually get 4 times more pizza. Remember that? Remember Jackson? Awesome. So area of the square is 18 squared. Is that 324? Okay. And we're going to find the area of the blue circle. When I say blue circle, I mean the circle, not just the ring of blue, everything inside of that blue circle, including the red, including the 10-point region. Okay? Isn't that pi times 9 squared? That's 81 pi. What happens if we subtract those? We get the area of the, if I do square minus this circle, I get the area of the 0-point region. Yes? All right, we'll do that, and then we'll finish up for today. 324 minus 81 pi. That's 69.53. Is the area of 0 points. That's the 0 points area. How do we find the area of the 10-point region? Just pi times 3 squared, right? Find out which one is greater. Does that make any sense? All right. I've already talked, we're just to kind of scroll ahead. We will finish this tomorrow, but to talk about experimental probability, it's the actual number of successes out of the number of trials. You're not going to write this down. We'll do it tomorrow. But if it talks about experimental, that's like me flipping a coin and getting the 3 tails example. All right. Let's check this homework and see if we can do them all. One's good. 3's good. All right, we're gonna do 1, 3, 6 through 8.
I like it when my numbers don't have shapes.
Is that all?
What about fake numbers?
And 12.
Valid, aren't they?
So tonight, everybody looking. 1, 3, 6 through 8, and 12, and I'll update it on the Canvas site.
I know you told me don't, but do you have the guide to notes from If you don't, that's fine. I can do it.
Hold on one second.